Every day we hear how software engineers and data engineers will lose their jobs. But fortunately, it's not true. So today, I will prove to you why data and AI engineers will be among the most in demand, highest paid professionals of the next decade, and why experts will be irreplaceable. I'm Lena, a Senior Director of Developer Relations at Akami. I help developers and companies with pragmatic AI adoption. Make sure to connect with me on LinkedIn. I often share practical tips and lessons on scaling data and AI solutions and getting real value from them. Data engineers today are the backbone of every AI system. You're essentially software engineers who collect, store, transform, and serve data at scale. You build the pipelines, you design the architectures, you ensure data quality. You're the ones who've been building reliable systems on top of unreliable infrastructure from day one. So, who are AI engineers? There are many definitions of that, but essentially, AI engineers integrate pre trained, hosted, or custom models and ship applications built with them. A huge part of AI engineering is actually making these models useful for your specific product. So you're taking your own data, documentation, product catalogs, customer histories, and making them accessible to the context of an LLM. So you're building systems that feed that business context into AI models. When I asked both Gemini and Claude Opus what percentage of AI engineering work is actually working with data, they both responded with 60 to 80%. So think about that. Most of what AI engineers do is data work. This includes building those context retrieval systems that make AI actually useful. So this means if you're a data engineer, you're already 60 to 80% of the way to being an AI engineer, and adding things like model integration to your data engineering skills is a natural evolution. It's not a career pivot. You already understand the hardest parts like scale, quality, reliability. So, how is the work of data engineers changing today? Think of our work as three distinct layers. At the bottom, we have the commodity layer, tasks that are becoming fully automated. Things like basic SQL query writing, standard dashboard creation, simple routine data quality checks. These are not differentiators anymore. Above that, we have collaboration layer, where AI augments, but it doesn't replace. Like a complex system architecture where AI suggests, but you decide. Performance optimization at scale, where AI identifies bottlenecks, but you understand the trade-offs. Business logic translation, where AI attempts to do the first pass, but you really catch the edge cases that could cost $1 million. So these tasks use AI, but they require your judgment. At the top, we have the strategic layer, skills that remain human. So things like multi-system failure diagnosis, where all of the different systems that you have, they point to each other. They are the reason for failure, but you're really the one figuring out what's right. It's like stakeholder trust and communication. Executives really don't want to hear from AI why their numbers are wrong. They need to ensure that the systems works right. Complex systems work, understanding why an old ETL process has a strange logic and what can or cannot be changed without breaking the downstream systems, and things like physical and digital integration, IoT sensors, manufacturing systems, anything that touches real world still needs human understanding of constraints that AI doesn't grasp yet. So now that we've seen all three layers, what does it tell us? Generating code is easy, but ensuring that it's correct in your specific context is really hard. So that challenge is an opportunity. So our value is in knowing when the AI generated or AI augmented solution will fail because we understand all the context that the AI may miss. So now let me show you how AI fundamentally changes data engineering. First, we'll talk about how AI is helping data engineers in their work. and then we will understand how data engineering is powering AI at scale. So data engineering is shifting from reactive maintenance to intelligent automation. There is a growing push to make systems more adaptive and resilient. Data pipelines have traditionally been brittle. A schema change or a bad record could break everything and require human fixes. Now, we can build systems that are self-healing to maintain that uninterrupted data flow. They continuously monitor their own health, they diagnose anomalies and failures, trigger remedial actions like retrying jobs, dropping or fixing bad data, or rolling back to a safe state. And in many tools now, when connectors encounter some schema changes, they self-adjust. When your pipeline breaks, AI doesn't just alert you, it suggests fix. And this approach is also relevant in the area of data quality, where there are agents, for example, tools like Monte Carlo data that use AI to automatically recommend quality rules and monitors and investigate root causes, suggest resolutions. When an anomaly occurs, it can investigate the cause across hundreds of hypotheses, like factual inaccuracies from the data source or coding errors, and provide explanations. The agent might say, this spike in nulls in this table is likely due to a recent change in this API, and here's how you might fix it. But behind the scenes of all of this is active metadata. We're moving from static, siloed metadata to active metadata that continuously feeds into tools and processes. Active metadata means using metadata like schema, lineage, usage stats, not just for documentation, but to automate and orchestrate data systems in real time. For example, if a table is flagged as sensitive, with active metadata, we can have an agent auto-classify the fields and enforce controls across BI dashboards and query tools without manual intervention. So your metadata is super important because it opens the door to intelligent control plane with dynamic capabilities. We're also moving from rules to semantics. So from fixed logic to meaning and context engineering. So traditional data engineering applies fixed logic like joins, filters without understanding the meaning of data. And AI changes this by enabling context-aware data engineering that uses vector embeddings and knowledge graphs to capture that semantic context meaning. This means that we can dynamically adjust or integrate data based on that similarity in content and relationships between concepts, not just direct matches. Then we're also seeing the rise of multimodal data. So getting structured data from unstructured data with AI as well. For example, in BigQuery, AI generate table. There's this useful function that we can call an LLM within a query with a multimodal input. So you can feed text or images and get structured results back all in one go. And under the hood, it calls out to Vertex AI Gemini model with your input and formats the response into a table schema that you define. So this brings tasks that used to require separate machine learning pipelines right into our data warehouse. AI is also accelerating the use of synthetic data. It is artificially generated data sets that mimic real data, solving for things like privacy, testing, data scarcity. And synthetic data generation tools use those generative models to create data with the same statistical characteristics and patterns as production data, but without the real-world sensitive content. We use synthetic data primarily in two areas, software testing and AI training. So a bank can generate millions of synthetic customer transactions to performance test a fraud detection system, just to ensure it covers scenarios like spikes in activity without using any real customer information. And testing teams can create exactly the data variations they need, like rare errors or extreme values. Modern physical AI, real-time and regulated use cases, they often require the lowest latency, highest performance, and built-in data residency. And that isn't achievable with centralized round trips to distant regions, bulk ETL, and like after the fact policy. So the shift is to move computation and frequently the models to the edge on the globally distributed network. As an example, in Akami, there is a global distribution of compute where we can run open source projects like Spin or SpinCube for WebAssembly functions running at the nearest point, and AI inference can run on open source models on NVIDIA GPUs close to users. As you've probably seen, we're also moving away from manual coding to force-multiplied productivity with engineering copilots. Of course, we know things like Cursor, GitHub Copilot, but there's also data engineering copilots like dbt Copilot, Databricks Genie. But here's where we need to understand with those. These tools are force multipliers, but they're not replacements. They assume we know what correct looks like. They assume we understand the business context, and they assume that we can catch issues when they are wrong. And here's the big thing that I'm seeing as well. Open source systems and protocols, they always win at setting the standard. So we see things like MCP and A2A transforming what workflow and agent orchestration can be like. And they're all open standards. We will see more development on that front as we haven't yet converged on quite a few things. The pattern is clear when you step back and look at it. We're moving from mechanical to intelligent data engineering. We used to react to problems after they happen, and now systems anticipate and fix themselves. We used to write rigid rules that broke whenever data didn't match exactly, and now our system can understand meaning and context. We used to be limited by whatever data we could access, and now we generate what we need when we need it. And we used to code everything by hand. Now AI multiplies our productivity by 10x. So now it's about building systems that understand, adapt, and improve themselves. We're really building systems that know what data means, and that allows us to do a lot more. We talked about how AI is helping data engineers in their work, and now let's talk about how data engineering is powering AI. Let me share what happened at OpenAI when they tried to scale their infrastructure. You would think that if any company could automate engineering, that would be them. They have GPT, they have world-class AI researchers. Here's what they actually faced. They had 37 different Kafka clusters. So engineers were asking daily, which cluster has a particular topic? And every service required manual setup, secrets, firewalls, everything. Their Kafka brokers were overloaded with connections. And here's what those engineers did. They looked at the situation and made decisions that no AI would make. They chose to give up guarantees that every textbook says are essential. They sacrificed ordered processing. They gave up exactly once delivery and partition affinity. And any AI trained on distributed systems best practices would probably flag this as wrong. But these engineers understood something that AI doesn't get immediately. Sometimes you need to optimize for different constraints. They used proxy layers like Prism for producers, uForwarder for consumers. They abstracted away complexity, so AI researchers could just focus on their actual work. Their Kafka adoption grew 10x. Throughput increased 20x. They now process 8 million messages per second with 5 nines of availability. They also migrated from 37 legacy clusters to 6 high availability cluster groups with no downtime. And the migration was transparent to users. It really took engineers who understood when to break conventional rules to build something that works at scale. So OpenAI discovered what they call a data flywheel effect. Fresher training data improves models, which drives more usage, which then generates more data. But that flywheel needs infrastructure that can handle that exponential growth. And that needs data engineers. So their production number really tell the story. And OpenAI made choices that go against the traditional distributed systems principles. And it works because those engineers understood that infrastructure really serves business outcomes, how to mitigate for the trade-offs that they're making. Because they're end users, AI researchers needed scale and speed, they chose this path. And these were the judgment calls that only humans can make. This is why data engineers are becoming more valuable. The lesson from OpenAI is that AI's success depends on data engineers that have enough expertise to make tough decisions, build sometimes unconventional architectures to create value for users, and keep systems running even when they violate the conventional principles. So even companies of the largest scale need engineers to solve these problems. They need experts who can see beyond the rules to what actually works. Let me address the elephant in the room, vibe coding. So for prototypes, totally fine. For data engineering, we should think twice before letting it run on autopilot. I worked with a team to help them fix issues after they tried a vibe coding strategy that went wrong. A team replaced their ETL pipeline with AI-generated code. Their transformation logic looked good at first. What it didn't know is that their source systems API returned microseconds as milliseconds for records created before a specific date. That was a legacy quirk from a database migration documented only in commit messages. So, and the senior engineer who initially handled this edge case was gone. And their inline comment about like pre-2019 records needing a correction by a factor of 1,000 was replaced by AI documentation about timestamp normalization. So for 3 weeks, all historical data was imported with timestamps that were off. And the monitoring showed green because the data was flowing. The row counts matched, but every calculation was corrupted. That was just the first problem. The AI had also generated their Spark streaming job with the windowed aggregation with watermarking, code that would make like any tutorial proud. But the AI didn't understand their data arrived from multiple sources with different latency characteristics. One source had sub-second latency, another source could delay up to 30 minutes during the peak load. And the monitoring checked for nulls and data types, but not for missing records that never made it past time. The AI-generated code handled the happy path. It worked with basic tests, but it really failed for their tasks in production. And in data engineering, every system has those undocumented behaviors, implicit assumptions, edge cases that exist nowhere in any training data for the LLM. These are not really bugs. They're just the reality of systems that only engineers who understand the context can handle correctly. So now you understand how our roles are evolving with these paradigm shifts. So let me show you why this really guarantees that your job will be the most critical in the next decade or so. I see the two fundamental approaches companies are making with their AI in their workforce. The first approach is driven purely by cost savings. Like, these companies assume that firing people today won't affect the quality tomorrow, and they're betting that AI can maintain their competitive advantage without human oversight. When you sacrifice quality for cost, you don't just lose customers, you lose control. And in critical systems like financial, healthcare, infrastructure, loss of control is potentially catastrophic. The second approach recognizes that competing today means maximizing the quality and execution speed. So these companies aggressively adopt AI to accelerate progress, but they never let go of people with the experience to make sure its correctness. So instead of layoffs, they are thinking strategically. How do we make our best people 10x more productive? How do we use AI to deliver higher quality faster? And the companies that succeed in AI, in the age of AI, they won't really be the ones that choose the best model because the model itself isn't a product. They'll be the ones with experts like you, hopefully, who can make those models work reliably, safely, and profitably.